Alright, so today we're doing a code review video on the game engine I'm working on for the past it's almost 7 months. I'll give a quick overview of the codebase organization, and you can jump to whatever part of the engine that you are interested. I will have timestamps in the video. So the basic unit of maintenance in this codebase is a module. Now these are not related to C++20 modules. In this codebase, modules are just compiled to a static library, so .lib on Windows, .a on Linux. Each folder you see here is basically a module, and they will be compiled to a static library. If you open a module folder, you will most likely see some subfolders. The lib folder is basically the module implementation, the source code, and it is going to be compiled into a static lib. Now, if the module is header only, then of course there won't be a lib folder and there's no static lib compiled. The next most common folder you will see is a test folder, which contains the source code for testing the public API of the module. It is a command line executable that links with the module static lib. Not every module has a test folder in it, but for more important modules, well, every module is important, but for very critical modules, we definitely have a test folder to validate and check for bugs. I'm using doctest. I think it's a pretty lightweight and pretty nice testing framework for C++. Occasionally, you will see a benchmark folder and a sandbox folder. The benchmark folder is kinda self-explanatory. It compiles to a command line executable that runs some benchmarks, and then the sandbox folder compiles to a usually GUI application. For instance, for my custom UI library, I have a sandbox application that I can run so that I don't have to recompile the entire editor to verify changes. In today's video, we are actually just going through all of the core modules. So LD core is like an interface library, and basically the runtime executable and the editor executable both links with this LD core library. Of course, the editor executable will have to define more modules because it provides more functionality than the runtime. And the runtime executable does not have to link with any of these editor modules. From the CMake file alone, it's not really obvious of the module dependencies, but basically modules that are defined later can use the functionality of previous modules. And we use some dependency injections to make sure that there is no cyclic dependency. So that's it for codebase organization. Feel free to jump to whatever module that interests you. Alright, so first of all, we have the header module here. This is mostly just macros and some lower order linear algebra stuff. So your vectors, which we will be doing SIMD, by the way. And there's also stuff like transforms and rectangles, all that common geometry stuff. They are in the header module. And of course, we have assert.h, which is just macro assertions. We strip out these assertions during release build, but for debug builds, it's pretty useful to just crash early and check what is wrong. There's also like this platform.h is a platform detection header, which is just defines what platform we are compiling on, what compiler we are using, and detects the CPU architecture, which is related to SIMD. The most important header is probably handle.h. This is, it's more commonly known as the pimple idiom. This is just a raw pointer, basically. It points to some object that is templated here. So we will see this handle type a lot later in other modules. A lot of the public API will use handle to kind of have opaque pointers. This opaque pointer handle isn't really about performance. In fact, quite the opposite. We're kind of trading one additional layer of indirection for reduced compile time. So the compile time does not cascade if we only change the underlying struct definition of T object. Then we don't have to recompile the entire public API. So the profiler module is quite simple as well. Currently, we are just using Tracy. Tracy is a pretty common profiler used in a lot of game engines, and where we can just give a demo. Here I already have a Tracy profiler running. We connect to localhost and we can run the editor here. and we can see Tracy kind of recording frames. Close it and we can zoom out, and basically this tells us how much time each function is doing across each thread. Here you can see this, that's the audio thread. And we have a job system, which we will discuss later in the job system module, and we can see like in each worker thread what they are doing, the asset loading jobs. And later during optimization, we will be basing our optimization around these profiling stats. Next up, we have the system module. This is super foundational. And here in memory.h, we have a wrapper around malloc, free, and new and delete. New and delete is actually just malloc and free with placement new and placement delete. Again, this is like C++ stuff, but for any large C or C++ codebase, you always have this layer where you map around malloc, where you can do guarantees such as making sure, like, oh, here we are asserting like standard malloc never returns null. This probably should not be an assertion. Usually there's recovery. We can try to free some memory and then call malloc again. And what's important here is like, okay, first of all, this has to be like thread safe, and then we're also doing some memory profiling. So the usage here is actually tracking how much bytes on the heap we're using for each memory usage. And the benefit of tracking this is like, by the way, in release builds, we can kind of strip this out. But the whole point of having this profiling layer around malloc and free is that we can kind of see if we have memory leaks very early. So for example, this is the editor application we just ran, and when we closed, I have a logger that basically tells me in what memory domain we are leaking heap memory. And of course, I know that I'm leaking in the UI domain because I'm just allocating some short strings and I'm too lazy to free it. I will fix this. But the point is, we know that there is memory leaks here, and we can fix this in a specific memory domain. So here I can like look at the UI code and make sure it properly frees everything. Now this could be false negatives or false positives. If you want the real truth, you would probably want to use external tools such as Valgrind. However, your executable compiled with Valgrind will be pretty slow. I forgot like how much of a slowdown, so that's usually not the best option. But anyways, it's just very common for bigger code bases, especially game engines, to just do profiling wrapping around malloc and free. And in the system module, there is of course the file system .cpp. Actually, C++ already has a standard file system, so this is like a very lightweight, not even abstraction. I think if we look at file system.h, I'm literally using fs path equals standard file system path. I just don't want to type that much. But otherwise, this is actually just an alias. There's also other stuff such as allocators. I think people call them arenas now. It doesn't really matter. It's just the point is that you allocate a large chunk of heap memory in a place, and then you manually decide how you distribute that memory. I think we only have two types here: linear allocator and a pool allocator. It's also called a chunk allocator. But yeah, currently I find myself only using these two types of allocators. Next up, we have the job system module. Again, this is yet another cornerstone module. There's a lot of ways to implement a job system. I'm just using a thread-based job systems, which is pretty much enough for my use case here. There's also a fiber-based job system for even more granularity, but I don't think I'm going that far. I think it's easier to just look at the profiling results to explain what the job system can offer. So for example, the blue part up here, this is the main thread. We can literally see the editor loading a project, the asset schema loading assets, and then here is the main thread using the job system to dispatch jobs and then waiting for all jobs to complete. So without a thread-based job systems, of course you can still build a game engine. Your main thread will just have to run all of these threads sequentially, and you lose a lot of concurrency. And one of the downsides of a thread-based job system is that your worker threads cannot wait for other jobs to finish. Your worker threads could dispatch jobs for other worker threads, but if you have one worker thread waiting for another job to complete, it's very easy to get into deadlocks. So that is one of the downsides, but it's not that difficult. We just have to be careful designing jobs so that a job does not wait for another job to complete. The command line module is just a small module responsible for parsing argv. So maybe we can start up the editor with command line options like Vulkan or OpenGL to kind of decide which graphics API backend to use. Currently, I haven't integrated OpenGL, it's only Vulkan. But yeah, that's something that we can supply to the command line, and this command line module is just a very lightweight parser. DSA module is for data structures and algorithms, which is for some custom templated data structures in the codebase, such as the vectors, strings, string views, all that stuff. Actually, I don't really have a vector template. This is a small vector optimization, which just contains some elements in place. I think LLVM also has a small vector class. I can't really remember. But yeah, this is just S vector class. I don't really have the default vector template class. I just use standard vector. And in the future, we would probably want to use our own hash maps. Currently, I'm just using standard unordered map, but it's not the best implementation. There are other implementations such as Robinhood, but anyways, I'll worry about that later. DSP module stands for Digital Signal Processing. It provides some biquad filter coefficients, which is used for low pass, high pass, and band pass filters, and alongside other effects. And it also has a resampling utility. So for example, when I import an audio file into the engine, we usually will try to resample it so that it's in the correct sample format, usually F32. So that the audio mixer can mix these audio samples easier. So this is very closely related to audio processing, which we will discuss later in the AudioBackend module. Next up, we have the serial module, which is of course responsible for binary serialization. Here we have the serializer, which can turn data in RAM into a byte stream, which you can then write to disk. Currently, the serializer uses Little Endian, but this is just an implementation detail. Doesn't matter if we use big or little. The point is that after we write to disk, we can perfectly deserialize this and load it back to RAM. So this is how we store assets or save files, anything like that. It goes through the serializer API. The serial module also prepares compression. Currently, we have Z standard and LZ4. Z standard has a better compression ratio, but LZ4 is much faster for decompressing. So for some assets, we would probably still want to do LZ4 compression. And here we have the Lexer module. A Lexer performs lexical analysis on source code and turns code into a token stream before constructing an AST. This could also perform lexical analysis on, say, SQL or CSS or any other language. And the reason I have a Lexer here is that I want to be able to eventually perform static analysis on Lua, because Lua is a weakly typed language. There's actually a lot of nasty bugs you can run into during refactoring. And the Lexer class we have here is just designed to be able to perform lexical analysis on a wide range of languages. And I should also mention Unicode support. Currently, we're only doing UTF-8. And for the UTF-8 decoder, I'm just stealing from Bjorn Homan. I hope I'm not butchering that pronunciation, but yeah, this is from Homan, and it's a very compact finite state machine for decoding UTF-8. Next up, we have the log module. And as the name suggests, we just perform logging throughout the codebase. And the way you use this logging module is that you can have static log, logger1, and you give it a channel name. And after that, you can just do in anywhere logger1 info, error warn or debug, the very common for levels of logging, and you put your format string here. Currently, it only logs to the console or the TTY, but I'm planning on making this broadcasting so that the log also appears in the editor console window. And I think it's currently not thread safe. Yeah, I still have to make this thread safe with mutexes because the log object is actually static, right? So it could be static or global, it doesn't matter. It's still not thread safe, so I will still need mutexes before I modify the log object. And you can connect to the same channel as long as the channel name is same. So you can have a static log1 from channel 1, and you can have log2 in a completely different translation unit, and it still connects to channel 1. Next up, we have the application module. Again, I'm already starting to think of renaming this module because the application module is essentially just providing window events to the user of the application, which is a very important distinction from other engines. A lot of engines in their application, like game loop is already hard-coded inside the application. But here, this application class actually only provides like an event callback, and whatever the user is will be processing that event and driving the event loop. So here's the poll events. We're currently using GLFW, so if we dive deeper into window poll events, it's actually just GLFW poll events, which on Windows it will just be the Win32 window, and for Linux I think it's mostly going to be X11 and Wayland. Wayland is getting pretty popular recently. Anyways, I'm thinking about just refactoring this application module into a basic window module, and the window module will just be providing the window events, because the events are also defined here, but these are only window events. And I'm thinking about putting event into its own module, so basically the event module. Currently, there are only two users of the application class. It's the editor executable and the runtime executable. So they have slightly different loops. And for the Lua module, this module actually doesn't deal with scripting just yet. This is mostly just wrapping the Lua state, which is a C API, into a more OOP friendly API. If we look at the public API, it's here, Lua state.h. So the actual symbol, Lua state, is just an opaque pointer here. We do not include the Lua headers in the public API here. So the Lua state class here is actually just a OOP abstraction. There's also other stuff like Lua module. This lets you define Lua modules in a more declarative way, I guess. And also Lua config, which allows you to write config files in Lua. There's also this Lua AST.cpp, which is like the compiler front end for Lua. We are using Lua JIT for executing the actual code, and the reason I have a AST parser here is simply because I'm trying to do static analysis on Lua later. So I still have to do all the Lexer and parser stuff. So the Lexer is actually from the Lexer module that we discussed earlier. And the parser here creates an AST so that we can do static analysis. So for example, I have a snippet here. Let's say we have a Lua script, and we kind of want to check for the type of the component that the script will be attached to, because Lua is a weakly typed language, so you could change the component type and then the script will just crash next time you run it. So a static analyzer will be useful if the script table actually declares the type. For example, maybe the script is for a mesh component, and then basically we can run a static analysis on this script. So we look at the final return table, it's representative of the script, and we look at the table called script and check what the type member it has. And then we can even report compile errors during build time. So we don't have to wait until we run the actual script And during attach, we figure out that the type is actually different from the actual type of the component. So yeah, an easier way is probably just use a strongly typed language in the first place. But again, we're using Lua because it's already pretty battle tested, it's easy to learn, and it's pretty beginner friendly. So that's why I'm kind of going the extra mile to even do a compiler front end just for static analysis on Lua. Next up, we have the media module. This is just for general purpose multimedia processing. And if we look at the include headers, the public headers of the media module here, then we can see it currently supports 3D model parsing, font parsing, bitmaps, which are just textures, audio formats, and of course we can parse individual formats here. These are mostly just using third-party libraries, and this media module will have to grow much larger as we support more stuff. And the reason why we have this multimedia module here is that later we will discuss this in the asset module. So imagine we're trying to import some asset, right? So if we want to import a .wav file, then we will first have to call the public API of the media module to parse the WAV file into samples. And then we will wish to resample the audio data in some way so that the audio asset is friendly for the audio mixer to process. The camera module is a pretty small module. So a camera in computer graphics actually just boils down to a few parameters. And its job is to provide a view matrix and a projection matrix. So depending on your camera, whether it's perspective or orthographic, you will have slightly different parameters. There's also a camera controller class here. It's just for you to control the camera easier, at least in the editor. For the actual game itself, you probably would want to write custom scripts to control the camera transform. I'll probably add 2D cameras later. 2D cameras is even simpler. It only needs a Mat3 instead of Mat4, and it has much less degrees of freedom, basically. It only has 3, in fact, a translation in 2D space and a rotation. Here we have the Gizmo module. It's just a very small Gizmo controller. This is a very tiny module. It only consists of this Gizmo controller. It's for 3D. We'll probably need another controller for 2D later. But yeah, this controller does not know anything about like 3D models or anything like that. It just has the user input the axis and plane of the transform and then start providing translation, rotation, and scaling. I should probably just run the editor and ignore the console window. It's work in progress. And yeah, basically you have translations and rotation gizmos and scale. I probably need to add local transforms as well. Currently these are all in global and it doesn't actually align to the rotation. But yeah, I'll fix that later. It's still a little bit buggy, so I'll have to do a lot of testing. Okay, so I'm assuming a lot of you jumped straight to this module. And for the next 4 modules, the RenderBackend, RenderGraph, RenderComponent, and RenderServer, these 4 modules are collectively how we draw pixels onto the screen. For the RenderBackend, this is just the graphics API abstraction. Currently there's only Vulkan. I decided to add Vulkan first because it's easier to integrate OpenGL or say DirectX 11. If I started with something like OpenGL, it's so much harder to squeeze Vulkan into the public API. So here we have the public API for RenderBackend. And at the public API, we will not see any Vulkan stuff because it's supposed to abstract multiple graphics API as its backend. And we will mostly be using this rhandle type. It's just a raw pointer to some object. So this T object could be some kind of opaque pointer. So for example, semaphores and fences. These are just raw pointers. The implementation is actually in semaphore object and fence object. And these two are for synchronizations. These are straight from Vulkan. They correspond to VK semaphore and VK fences. And these are mostly used for fences, it's for CPU and GPU synchronization. And for semaphores, it's synchronizing work that is on the GPU already. Again, once we add OpenGL, this probably doesn't matter because OpenGL doesn't even let you do a lot of synchronization. Oh, actually, there's memory barriers, but we'll get to that later. And of course, a lot of these mostly map to Vulkan stuff, Vulkan structs. And image splitting buffer. Okay, so buffers. Here you just supply the usage of the buffer. If we look at the enum flags, we're just declaring what are we going to do with the buffer. It's usually either a vertex buffer or an index buffer. There's also like storage SSBOs, all that stuff. And transferring this is also Vulkan specific. In Vulkan, we will do staging to upload data from the CPU to GPU. And similarly, we have image. And this is probably the first important decision, that is the sampler is tied to the image. This is because we're going to add support for OpenGL later. And OpenGL, the images are actually called combined image samplers. And as the name suggests, the sampler info is actually bound to the image or the texture you are sampling from. So yeah, this is kind of just future proofing so that I can add other graphics APIs easier into this backend. And of course, there's image. There isn't a big difference between images and textures. Usually textures are just images with sampling info, but it's just the different semantics. And the public API, yeah, I just realized this looks like a struct with no members, but actually it just inherits from the handle, which is a roll pointer, so 8 bytes. And below we start to see render pass stuff. So render pass, it's not a thing in OpenGL, but it's a very concrete object. There's a VK render pass that you have to create and manage explicitly. In fact, the render pass is so fundamental that if you want to create a frame buffer or a graphics pipeline, you actually need to define a render pass first. And a render pass is just the context of which the color attachments are going to be used during a scope of rendering. So here you can see for color attachments, you define their color formats, load up, store up, their image layout. And of course, image layout is another Vulkan thing. You don't have to do image layout transitions during OpenGL. But in Vulkan, you have to track the layout of different images, and they can change. So there's a specific layout for sampling and another specific layout for transferring, and also specific layouts for other operations. So yeah, you declare how the color attachments or depth stencil attachments are going to be used during a render pass. Oh, there's also a resolve attachment, which is mostly for MSAA. And then you declare render pass dependencies. And finally, the render pass info that contains all the information that we just discussed. And this is actually a simplified version of the Vulkan render pass. Did I mention that Vulkan is kind of verbose? Okay, and there's also, of course, the clear color and the clear depth stencil value that you have to declare even before using the render pass. So it's here. It's the render pass begin info. Yes, we have a separate info for beginning a render pass. Yeah, this is still a simplified version of what Vulkan has to offer. And finally, we got to the shader API. It's just shader type. Currently, we only have 3 types, I think. Yeah, it's the vertex shader, fragment shader, and of course, the compute shader. And currently, we don't have any public APIs for shaders, and it's just a roll pointer. We create and destroy resources from the render device, which we will see very soon. So a set corresponds to a group of resources, a group of bindings of resources, actually. And you allocate them from set pools, and set pool is its own resource that you have to create and destroy. Again, this only makes sense if you're familiar with the Vulkan API. And of course, you have to describe the layout of your graphics pipelines, which is just the individual set layout. And of course, describing vertex input through attributes and bindings, and a series of structs for describing pipeline states, for rasterization, for depth stencil states, for how the color attachments blend, all that stuff, and collectively they form a single pipeline info. And then we create graphics pipelines with a pipeline info. And a compute pipeline is much simpler. It has much less state than a graphics pipeline. And you just supply a single compute shader to create a compute pipeline. And the actual structs for draw calls, for drawing vertices directly, and then for drawing indexed. So this is like GL draw elements. I think in OpenGL it should be called like GL draw arrays. I'm not sure. It's been a while since I used OpenGL. But yeah, and of course memory barriers for buffers and images. This is also a Vulkan thing. But actually, there are also memory barriers in OpenGL. If you are doing some stuff like persistent mapping, then sometimes you have to insert your own barriers in OpenGL. But in Vulkan, everything is explicit. Like you as the programmer are supposed to insert every single barrier in the right place at the right time to make sure there's no corruption or data hazard. And the command list in Vulkan, it's actually called the command buffer. It's just a buffer of commands that you record before you send it to the GPU. The command list is actually more of a DirectX naming convention. I think it makes more sense. Like it's just a list of commands. So basically between begin and end recording, you append commands into the list. So that could include binding the graphics pipelines, compute pipelines, and like using what vertex buffers, index buffers, and dispatching if you're using compute shaders. Of course, there's the scissor stuff and the actual draw calls, draw and draw indexed. There's a lot more draw calls that I have to implement later. And of course, inserting memory barriers. So this is still a very low level module. The user of the LDRenderBackend module still has to insert memory barriers explicitly. And that's about it for the command list. There's still a lot more commands I have to implement later. And of course, the command list needs to be allocated from a command pool. And once you have enough command lists, you submit it to a queue for execution. So here's the queue, and you can submit work to it. A fence, which if you recall is for CPU and GPU synchronization. Once the work is done on the GPU, this fence will be set, and we can check if the GPU work is done from the CPU side using this fence. There's, finally the render device, which is just here for you to create and destroy resources, which we covered most of them. This is still a simplified version of the full Vulkan API, but it maps very closely to it in a way that I can still add OpenGL or other graphics APIs later. And so the implementation for the public API here is rbackend vk.cpp, which is just the Vulkan implementation of the public API here. So for the first release of this engine, I will only be supporting Vulkan and OpenGL for desktop. I could have used some libraries such as BGFX, Diligent Engine, and NVRHI. So all the Vulkan stuff is actually just in this single file. It's not even like, it's not too bad. Okay, so the next module on top of the render backend is the render graph module. And the render graph is actually just a system for scheduling work and managing synchronization automatically. Because the audio backend is still very low level and you have to do GPU side synchronizations yourself. So the render graph kind of does that and also tracks some other states, such as the image layout. And we also have the idea of a render component. So a render component would contain multiple graphics paths or multiple compute passes, basically. I think this is analogous to like a single graphics algorithm. So if you think about something like blurring, a lot of blur algorithms actually consist of a few downsample passes and the same number of upsample passes. So later we will see a render component called dual Kawase blur, and inside that component, basically we have multiple downsample passes and multiple upsample passes. And each node in the render graph is just a render component. So immediately, a huge benefit of having render components is that we can kind of maintain individual GPU algorithms in its own component, right? We just declare its input and output images or buffers, and that's it. We can kind of glue together different components as long as the input and output matches. So it's much easier for testing the components. Okay, so next up, the render component module is where we actually start designing the renderer. So a lot of graphics pipelines, compute pipelines, and algorithms are defined here. For example, the dual Kawase blur is just implemented as a render component with multiple downsample passes. So I think, yeah, when we add a component to graph, what are we doing? So inside a for loop, we're downsampling, so we are decreasing width and height by half and adding a downsample pass. And similarly, later we'll have to do upsample. And it's also another for loop, and we increase the MIP map level. And then add upsample passes along the way. So the render component is a really nice way to just define individual graphics algorithms. There's also stuff for like outlining and the forward rendering stuff, drawing the overlay. There's also screen picking. So screen picking is actually just implemented as a single compute shader here. So yeah, screen picking is a render component with a single compute pass that calculates what the texel is under the cursor. Finally, the RenderServer module. This is the top-level graphics abstraction. Similarly, later we will discuss about other modules such as AudioBackend, AudioMixer, and AudioServer. AudioServers and RenderServers are like the top-level API that the game scene communicate with. So the game scene will not be calling any APIs from the lower-level render backends. The RenderServer provides even more dependency injections to draw the game scene and sometimes the editor. And if we are using the final runtime, then obviously we do not have to deal with these editor drawing stuff. We will just draw the game scene itself and then maybe some screen space UI. So these two passes are only used. So the next three modules are AudioBackend, AudioMixer, and AudioServer. These three modules are the audio subsystem, and for the audio backend, I'm using a library, a pretty famous audio library called Mini Audio. And the job of the audio backend is to basically provide a data callback so that we can write frames to the audio card. Now, the audio backend does not care about how the frames are mixed. That's the duty of the mixer module. The audio backend only provides a callback, which is going to be called on the audio thread, and it's going to be resampled on the fly to whatever native audio API. So on Windows, this would be WAS API, Windows Audio Session, and on Linux, there's quite a few, with ELSA being the most famous, I think. There's also PulseWire, or is it PipeWire? I'm not sure. I'm not a audio programmer by trade. So Mini Audio basically takes care of this abstraction layer for us, and we can provide a very clean API for the audio mixer to generate frames to this callback. Okay, next up we have the audio mixer module. And from here on, I'm trying to write my own solution for audio mixing. And audio programming is pretty special in the sense that the audio thread should be non-blocking without using mutexes. So I'm currently using a command queue that the main thread can continuously push commands into it, and the audio thread will execute the command before mixing. And I'm using a lock-free queue by Moody Camel. And basically, the audio command is how the main thread can describe its intent, and the actual command is always executed on the audio thread. And I'm also starting to mess around with audio effects, which is basically just DSP, digital signal processing. We already have a DSP module I mentioned earlier. It's also common to have a double buffering setup, a ring buffer setup. So there are copies that the audio thread is writing or reading to, and the other copies could be manipulated by the main thread or other threads. So currently in my audio mixer, the main thread just pushes audio commands to a lock-free queue. We'll see how this scales. And there's also a very important design decision is that whether or not we enable effect chains on individual playbacks. So most game engines and also for digital audio workstations like FL Studio, you have buses. You have audio buses that you can send frames to. And then you usually have the DSP chain on individual buses. So I'll definitely add that later, maybe not in the first release, but for maximum flexibility, I think I probably would allow DSP chains on both individual playbacks and on audio buses. So for example, Godot has audio buses, but you can't really set effects on individual audio playbacks. It's called an audio stream player node in Godot, but you can only apply effects to audio buses. So you kind of create a single bus for the playback that you want to add an effect for, which isn't bad, but I just want to give like maximum flexibility to the sound designers. And finally, we have the audio server module. So this module is the top level abstraction for audio subsystem, similar to the render server, it being the top level abstraction for rendering. And basically the audio server is going to be accessed on the main thread. And all these public APIs just pushes commands to the audio thread and controls the audio mixer that we described in the audio mixer module. So currently there's not a lot of functionality. I'm still working on this. I've only started working on the audio subsystem like a few weeks ago. So there's still a lot of work to be done. Okay, next up we have the UI module. And as a quick reminder, all of the modules described today are still part of core modules, which means that these are all libraries that can be used by both the runtime and the editor. So this UI framework is basically just a small library that is used to render both the final in-game user interface and the editor UI. And the organization is pretty simple, at least I think it's simple. So basically you have a UI context, and inside a context you can create UI windows, and each window is a widget tree, which is just an hierarchy of widgets that you can edit. So a widget hierarchy is pretty popular or even expected in all these game engines like Godot, Unity, Unreal. They all have a widget hierarchy for the user to add scripting logic to it. So this is basically the backbone for the UI system. Now, I want to point out the UI layout logic is based on a video by Nic Barker. I will have a link in the description below. It's a banger video. It's the cleanest design I have seen before. I've also tried to do my custom UI layout stuff prior to beginning this game engine. And I was very lucky to find the video by Nic Barker. It is a very concise UI layout logic and pretty fast as well. And I'm just re-implementing it in C++. Next up, we have the asset module. And of course, this is all about asset management. I could probably make a whole video on asset manager alone, but basically the asset module will define the dimensions of different assets. So for audio clips, mesh texture 2D, and even scripts, that's also an asset. And it defines ways that you can import and load. So an asset needs to be imported during the editor, and also the runtime needs to understand the asset format so that it can actually load the assets for the game, right? And one thing worth mentioning is the asset schema. So the schema is basically just a text file that describes the assets. So we will have a text format and also a binary format that is optimized for runtime loading. So for the text schema format, I'm currently using Toml, but JSON and YAML are also very common for game engine asset schemas in general. And basically, the schema will describe the version and the parameters of the asset so that we can migrate assets from an older version of the engine to a newer version. This schema should contain enough information for the runtime or the editor to load up the assets. And next up, we have the data registry module. And the data registry is analogous but different from ECS. So as I described in my previous videos, a scene in my engine is just a tree or multiple trees of components. So it's actually similar to like Godot nodes or even Unreal. So basically the data registry is in charge of the allocation and lifetimes of all these components. And currently the components of the same type are allocated contiguously. So if we iterate across the components of a same type, it should be very cache friendly. And the tree hierarchy is just for organization. We don't really iterate through the tree. We only do that when we are figuring out the transforms. So the transform of a child component is always relative to the transform of its parent. Other than transform invalidation, we never iterate through the tree. So yeah, this is very important for performance and probably have to do a lot of testing and profiling. And finally, the scene module. So the scene is actually starting to feel very high level because it's integrating a lot of subsystems. So it uses the data registry to organize and allocate components, and it also needs to use the asset manager to stream assets, and of course other audio subsystem and the rendering subsystem, and it also has a Lua state because we are using Lua for scripting. There's still a lot of stuff to be added, for example, networking. I don't think we would be doing networking soon, at least not in the first release of the engine. Okay, and similar to an asset schema, we also have a scene schema. So a scene schema is basically just a text file. We are using TOML for our schema format. And basically we just read the TOML file and look for what components we are going to load. Again, this is mostly for the editor. For the runtime, we probably want to compile the schema into a binary format. So the end players will not be able to just mess up your scenes too easily. They still could, but they have to reverse engineer a little. So yeah, an asset schema is a file with enough information to fully describe the scene hierarchy. And finally, the last module we are going to cover today. It's the project module. And it's just all the metadata that is in a game project. So for a project schema, it needs to be able to describe the full project. So it's going to reference all the scene schemas in the project and all the assets used in the project, as well as any other information required to fully describe a game project. So yeah, an editor will modify the project schema and the final game that you ship will just load the project and start up the main scene. Okay, so that's about it for the past 6 months. It's definitely less exciting or graphically advanced compared to some other game engine devlogs you can see on YouTube, but I'm mostly trying to get the foundations right, so I really haven't focused on one specific subsystem. I do intend to release the engine at some point, but I want to set expectations. The first release is going to be very minimal, only capable of making some small 2D games like Pac-Man. Obviously, I'm not going to compete with any big engines out there like Unity, Unreal, or Godot. I'll probably make a roadmap to first release kind of video at some point, and keep on sharing the progress on YouTube. So if you're interested in seeing more game engine devlogs, please consider subscribing, and hopefully someday someone other than me is willing to make indie games with it.